I would like to thank the organizers for giving me the opportunity to talk here. So today we are going to discuss this topic known as controllability of wave equations, and one of the methods to solve them is Carleman estimates. So we'll look at how we can use Carleman estimates to solve controllability. So what we will first do is just look at a basic idea about what the control problem is and some of its applications in real life. Then we'll move on to the finite dimensional case. After that, we'll look at the problem in the context of wave equations and how they can be solved. And also, finally, we'll look at some of the recent results that we have obtained. So, what is the basic problem that is considered in control theory? It is the following: that can we drive the system from a given initial configuration to a chosen final configuration using a suitable control function. So, if you want to understand this in a better way, you can just look at this picture that is here. So this was drawn by one of my friends. So let's say that you are at some point A and you want to go to some point B, and you want to drive your car to go from A to B. So in this system, the steering wheel and the accelerator, brake and clutch system will form the control, and we know that this can be actually done by using this kind of control here. So this is a very basic example, but this kind of tells us the main idea behind control theory is that you are somewhere and you want to go to some other place. So how do you do that? And if you think about it for a bit, then this has many applications in real life. So I'll just show some of them. So firstly, it is used in flying of aircrafts. So if you want to go from your origin to your destination, then control theory is used to basically figure out what the path of the flight will be, and also to maintain the alignment of the flight in the whole path. And over here, this is something that comes from chemical engineering, I guess. So suppose you have extracted some raw natural gas from below the earth, and you want to extract different kinds of product from it, like petroleum, kerosene, and all these products. So over there also, its control theory is used. Over here, we have an example from biology or medical sciences. So this process is known as a drug delivery mechanism. So what happens is that suppose you give medicine to the patient, and you want to make sure that the medicine actually goes and acts on the specific organ that you want. Maybe you give the medicine over here on the hand, and you want the medicine to go and act on the heart. So how do you make sure that this happens? Over here also control theory is used, and this is an example from robotics. So perhaps the hand of the robot initially is it's closed, and you want the robot to open their hands. So this will be the final condition. So over there also control theory is used. And finally, we have an applications in financial maths as well. So it is used to study stock markets. So now this has become very common for people working in control theory to show some examples initially, and then there will be no more example applications. It will just be theoretical. So that's what we will do here as well. So coming to the theory part, if you consider the control problem, there can be different notions of it. So if we want to go from any point A to any point B, then that is known as exact controllability. If you want to go from any point A to the origin or 0, then we say that that is null control. So it can be either A to 0 or 0 to A. Both are considered as a null control problem. And perhaps due to whatever reasons depending on the system, maybe you are not able to reach exactly B, but you can get really close to B. So basically an epsilon ball around B. Then we will say that this is the problem of approximate controllability. So there are three notions: exact, null, and approximate. Depending on the system, they can be equivalent. They usually are not, but sometimes they can be. In case anyone is interested in learning more about the basics of control theory, then you can just put an online search for this. And these are really good notes. They are freely available online. So if you want to get an introduction, then you can search for these notes by Zuazua. So with this, I'll just briefly mention what the result is in the finite dimension case. So over here, we will consider a system of this type. So y dash is ay plus bu, and some initial data y at 0 is y0. So I have written the spaces here, but if you don't want, then you can ignore the spaces. So we'll just give an overview, which is in this system, y is known as the state of the system. This u over here will be the control that we want to find. And we say that the system is exactly controllable in time t if given any y0 and y1, there exists a control in some space such that y at capital T is y1. So what this is basically saying is that solution of this system should be able to reach y subscript 1 at capital T time. Okay, and you can see here that we have y running from 0t to Rn and u from 0t to Rm. So the reason for taking m and n different is this is something that is motivated from real life applications. So what happens is that if you are given some system and there are n components, you don't want to put control that is also m dimensional control. So you usually want that there are less number of controls. So one quick example would be that if you want to put air conditioning in this room, I don't want to put air conditioning throughout the room, right? It's just in one place, and from there I want to control the temperature of the room. So it is something similar. So if you have, let's say, 10 components, then maybe you want to put 3 or 4 components control only. So that's why this is a slightly more general type of problem. So we consider control which is less than equal to the number of states. Okay. So we'll consider some examples for this. So if we have A to be this matrix and B is 1, 0, then we can write the system y dash ay plus bu in this form. So y1 dash is y1 plus u and y2 dash is 2y2. So maybe even if you don't solve the system, you can directly look at this and say that clearly u is not at all present in this second component. So you may guess that this system is not controllable, and that is indeed true. So the solution for the second component is given by just this expression. So the y02 comes from initial data and then e power 2t. So basically, no matter what happens, y2 is always going to be in this subspace generated by e power 2t. So if I tell you that I want to reach somewhere which is outside e power 2t, you will never be able to reach there. So that's why this system is not controllable. Okay, and this is kind of not really a very well coupled system. That's why it gives not controllability. But you can of course find more complicated examples. Like properly coupling is there, but still you are not able to show controllability. In the next example, we'll look at this matrix. A is this type and B is 0, 1. So then the system reduces to this y1 dash is y2 and y2 dash is ut. Now let's say I want to go from this point 0, 0 to 1, 0. Then what we want is basically find a function which satisfies these conditions. So y1 at 0 is 0, y1 dash at 0 is 0. So the first 0 and 0 give me this 0 and this 0, and the next 1 and 0 will give us this 1 and this 0. So now you are asking whether there is a function which has this condition that at 0, value of the function is 0, derivative is 0, and at capital T, value is 1 and derivative is 0. Clearly, there are infinitely many such functions. One such choice could be you can take ut to be z double dash, where zt satisfies this. So now you can check that this ut will actually be satisfying this thing, and it also satisfies the condition that is needed for controllability. So this u will help you in going from 0, 0 to 1, 0. And there is nothing special about like 0, 0, 1, 0. If you are given any arbitrary 2 points, you can similarly find some other control which will work there. So we will say that this system is controllable. Okay. Right. So by now, finite dimensional control theory is very well understood, and this is due to a wonderful result by Carleman, which says that the system is controllable in time t if and only if rank of this matrix is equal to n. So this is a very good algebraic condition. This is a very big matrix, but that's not the main part. It just shows such a nice condition that if this rank is n, then we will say that the system is controllable. So some facts about this matrix is that this matrix is an n cross mn matrix, and you can see over here I have some condition on time t, which is saying that control is controllable in time t if and only if. But in the second part there is no condition on time t. So what this means is that if it is controllable, it is always controllable. You don't need to worry about time of controllability. But for PDs, problem is much more difficult because we don't have any such condition. And again, this time of controllability will be important for some PDs, not all. We'll look at like in the subsequent part of the talk, we'll see that when it is important and when it is not. Okay. So now we will move on to wave equations, which is what we have been doing. So 1 plus n dimensional wave operator is given by this square, which is minus del t square plus Laplacian x. So this is just a convention thing. I think sometimes people use del t square minus Laplacian. Then everything in the rest of the talk will be join with a minus sign, but for us we will be considering it as minus del t square plus Laplacian. And all the results that we have been trying to do is to basically get control results for the most general types of equation on the most general types of domains. So that's why we'll consider not just box, but also box plus some lower order terms. This is the first order term, which depends on this vector field x and some potential term v. So there are conditions on what x and v will be. We'll not be worrying about all those things now. So for the rest of the talk, whenever we write L, we will mean that this general wave operators, box plus lower order terms. And why are we interested in studying waves? It's because wave equations are kind of the first hyperbolic PD that you study, and they basically serve as a model for other hyperbolic PDs as well. So any result that you obtain for waves, they are going to be useful, mostly useful for studying other hyperbolic PDs. And next point is that everywhere around us, you see, you are going to encounter waves. Even the way that I'm talking to you and my sound waves are being transferred to you, that's also done by wave equation. So it's really useful if you are more interested in applications as well. So to talk about the control problem, we first need to know what the initial boundary value problem is that we'll consider. So for that, this is the problem that you have, which is wave operator acting on y is 0. You have some initial condition y0 minus y1 minus and some boundary condition which is f. So this is illustrated here, which is basically saying that you have some initial data here. You are putting a boundary condition f, and then you let y evolve inside the cylinder. So this is basically this region minus t comma t cross omega is the cylinder. And by now, well-posedness of wave equations is very well understood. So for smooth x and v and initial data lying in some space and a suitable function f, this above system has a unique solution y. Okay. These spaces will be important in some parts of the talk. I'll talk about it when it's important. For now, if you are not, I mean, you can ignore it if you want. So initially is that can we drive y to a desired state? That is our goal. So pictorially speaking, you are given some y0 minus y1 minus. Then you want to find the control function f so that at the final time you are able to reach this part, y0 plus and yn plus data. So this is the definition that let's say that gamma is some part of the boundary. I'll talk about why we have a subset of the boundary again. So for any initial and final data, can you find a function f such that solution of the initial boundary value problem is satisfying this condition that at capital T you are reaching y0 plus and y1 plus. So again, why we have this subset is because, as I gave the air conditioning example, you most of the times you don't have access to all the components of the system or all the domain. You can only affect a part of the system. And this is something which is known as boundary control, because you are putting the control on the boundary. But there is another notion called interior control. So over there, instead of the boundary, you may want to put the control on a subset of the domain. So over here, maybe we were putting the control, let's say, on some part like this. But in interior control, you may want to put control somewhere here. So that's something which is known as interior control. Sometimes they are related how to solve them, but not always. Depends on what kind of PD you have. Yes. Yeah. So instead of there it will be like this. So this is like indicator, and then if I say this is omega, then it will be. Okay, so a few remarks about controllability of wave equations. Question? Okay. So if either the final point is 0 or the initial point is 0, then we will call it as null controllability. And wave equations have this really nice property that they are time reversible. So null and exact controllability are equivalent. There's a very quick intuitive proof for this, which is clearly backward implication is true, right? If it is exact, it will be null, because this is a stronger stronger result. And if you want to do null to exact, so what you want is, let's say that I want to show, so if I have null controllability, I want to show exact. So for this, you are given any 2 points A and B, and you want to show that you can go from A to B. So what I will do is use this. So you can go from A to 0. And again, using null, I know that I can go from B to 0 as well. But because waves are time reversible, this means that you can go from 0 to B as well. So to go from A to B, you go and then 0 to B. So that's why null also implies exact, and because of this nice property, solving control problems for wave equations is slightly easier in some sense. And the other thing is, because wave equations have finite speed of propagation, you need to wait. So the time of controllability is, it should be large enough, so that if I put the control here, then it needs sufficient amount of time to reach everywhere inside the domain. It cannot be done in like small time. And quick comparison with heat equations is that heat is not time reversible, so it has a smoothing effect, because of which you do not expect this condition to hold. That's why most of the times people only do null or approximate controllability for heat. Exact controllability is not a, it's a very difficult problem, and very recently some results have been done to get not exact controllability, but slightly like the best possible thing that you can do for heat equation. And again, they have infinite speed of propagation in heat equation, so there's no concept of time t should be large enough. Over there, if it is controllable, it is controllable in arbitrarily small time. Right. So now we will see like how do you solve this control problem. So this is what we want, right? Given any y0 plus y1 plus, we want to find a control function f. So if I say like define this script f map, which runs from the space of controls to the space of like where you want to reach, then I want that this has to be surjective, right? So which will basically mean that no matter what point you give, you can find a control which will make you reach there. So I want you to remember just this part, that some function has to be surjective. We'll come back to this after 2 slides. So why am I talking about this? It's because of due to this notion of duality, which is basically you take the original system and then find the system dual to it. So what is the system that we had? This is the control system, and then this is the adjoint system to that. So Ly is 0 will give us L star. I don't care what L star is, it's some adjoint. It looks similar to the wave equation, it's just some signs are here and there. Then you have corresponding initial condition, and then same boundary condition is like this. And so because of the spaces we have, the solution y that you get is known as the ultra weak solution, or also sometimes people call it solution by method of transposition. And over there, this is just the weak solution. And the script f that we saw in the previous slide was running from this space to this space, and correspondingly f star will run from the dual space to that. And you can find what the adjoint of this script f will be, and it turns out to be this Neumann operator acting Neumann data of phi. Okay, so why are we talking about all this adjoint business? It's because of a result from functional. Yes. Okay, so okay, I'll write this. Okay, so remember 2 slides ago we said that controllability is equivalent to f being surjective, and using a very good result from functional analysis, we know that a function is surjective or map is surjective if and only if its adjoint satisfies some kind of inequality. Okay, so now what we have done is we wanted to show some surjectivity property. Now it has become an injectivity problem, and for our setting, this problem is just this showing this inequality. So that is what f star xi was, and this is just xi over there. Okay, and this inequality is known, what is known as observability inequality, and so corresponding to this, we have this notion of observability as well. So observability problem, which is known as that. And what is the observability problem? It is whether you can show an inequality of this type for all phi naught phi 1 in the corresponding adjoint space. Okay, and I'll just write this because we'll refer to this. Okay, so in case actually you don't have to remember what this is, just remember that you want to control energy of the initial data by the thing that is being observed. Okay, so why are we bothering about all this observability thing? It's because of a result by Dölecki and Russell, which basically said that studying the controllability of the original system is equivalent to studying the observability of the adjoint system. And why is this helpful is because if you recall the definition of controllability, it says you are given 2 points and you want to find a control which will take you from the initial to the final point. And this is a very qualitative definition. So if I give you some random system, you don't know how to find this control. However, this is just an estimate, right? And in maths, we have like several tools to prove estimates. So that's why this quantitative thing is a much more approachable way to solve the problem. So in the rest of the talk, whenever we say we want to solve the control problem, we will be talking about this observability problem. Of course, there are other constructive approaches to solve controllability, but they are like very less applicable. Most of the times, people just worry about solving observability. And another result that should be mentioned here is this work developed by Lyons in 1986, which is known as Hilbert uniqueness method. So you basically construct some special Hilbert spaces, which basically gives you actually. So this is just showing what that these two are equivalent, but Lyons result gives you how do you find the control. Okay, and the control that you get from using HUM method by Lyons is actually the control with the least norm. So this ties to this notion of cost of controllability, and cost is not just financial; it can be anything depending on what the system is. Sometimes it could be finance, other times it could be like time of controllability. It's up to you how you define it. So it all depends on what the system is. So whatever control you get from HUM method is actually the one with the least L to the. Okay, now we'll look at some of the methods and also literature surrounding this control problem that we have mentioned. So one of the first methods that was used to solve control problems is this approach known as multiplier method, and this was so mostly this is only applicable to equations of this type, so you don't have any lower order terms. So this is a very specialized kind of approach, and as the name suggests, so what you do is you take some special type of multiplier. We will see at least one case of like what the multiplier is, and then you do integration by parts and you use energy estimates and then try to prove this kind of observability. And so some of the results in this direction were obtained by Ho and Lyons. So again, HUM method that Lyons developed was from this paper, and other people have also developed on this. But so we will look at what Ho and Lyons have done in a few slides. But I'll just mention this that this is a very like, although it was the first method that was used, it's very specialized. So you can't expect to use this method to solve control problems in the most general sense. Another method that has been used for solving control problems is microlocal approach. So the good thing about microlocal techniques is that the control regions you get, they are the best possible you can get. So in terms of whether it's the smallest control region and also in terms of like best possible time of controllability. However, the bad thing over there is that these PD coefficients that you have, they can be time analytic at best. So if you don't have analyticity assumptions in the time component, then you cannot do controllability using microlocal techniques. So we are again not using this because we were trying to solve it for most general equations without any analyticity assumptions. And I'll quickly mention, so a lot of work has been done in this direction, but I'll just mention this work by Barnos, Lebo, and Roche, who kind of found the most like using microlocal approach obviously, but they found out what's this notion called geometric control condition, which kind of gives you a like relation between the control region and how long you have to wait to get controllability. So I cannot draw the figures in 2 dimensions, but if you have, let's say, a string, so let's say 1 dimension is there, and I'm putting control only on this right component. So I put the control here like this. Then what it says is that so every ray of like every light ray that is inside the domain should meet with this region within the time of controllability. So basically what it says is if I have a light ray which is going like this, then clearly this will meet this region. So okay, you are okay with that. But if I have a light ray which goes like this, and so if it's not in this direction, it has to go back and then reflect it from the boundary and then try to meet here. So what will happen is that it will try to come back here. So clearly if you wait, so if you start from here and you wait till here, you are not going to get controllability in this type of setup. So what you want is then you have to wait for longer. So you have to extend till here, so that any ray that is there will actually go and meet the control region. So now this part is controllable, but the previous one we had, which was just this part. So if you just wait till here, it is not controllable. However, if you wait till here, this will be controllable. Okay. Similarly, you can draw different figures for 2-dimension. You can actually look at this paper. They have different, I think 5-6 figures are there, and it's really interesting. Like you can have controllability and not. So basically, in 2 dimensions, if you take a figure like this, so you actually need to put a control here as well. Because if you don't put, there's some light ray which will be reflecting between this, and then it will not be controllable. So there are like many different weird shapes in the paper which talk about these things. But again, because of this disadvantage, we will not be using micro-local approach. Finally, Carleman estimates are another approach to solve control problem. And good thing about this is they are applicable for the biggest class of PDEs without any analyticity assumptions. However, if you are gaining something, you are also going to lose something, which is the control regions you get are not the best possible ones. So micro-local or the GCC approach is the best control region result. It's not a big thing because anyway, we were going to solve it for the most general class of PDEs. So we will not be bothered about not getting control regions, best control regions. And this was first Carleman estimates in the context of controllability for wave was first done by Fursikov Manubila. There are other results as well. I'll just talk a bit about this result and this result. So the result by Fu, Yong and Shang in 2007, over there they have solved a problem of this type. So we will come back to this maybe towards the end of the talk, why this is important. So they assume that there are some conditions on AIJ, some electricity conditions, and also there is you assume existence of a suitable distance function. So maybe this part will not make sense now. After we have seen a few more slides, it will. And some of the things that I'll talk about now are closer to this result that was obtained by my PhD advisor in 2019. So over there, he solved a boundary control problem for wave equations on time-dependent domains. So when I was talking about solving control problems for for the most general waves and on the most general domains, this is what we meant. Like you have wave operator plus lower order terms without any analyticity assumptions in time, and also that the domains and everything has to be time-dependent. Okay, so what is the benefit of using Carleman estimate? So these are some estimates that were developed by Carleman in 1939 that were mostly used to prove unique continuation results. So initially they were only for elliptic PDEs, but later they were developed for hyperbolic PDEs as well. So essentially they are weighted estimates of this type. So there is some kind of energy here and some e power AF weights, but you can see that this is kind of hidden inside this, the observability that we have. I don't know if online people can see this, but the observability we had earlier. So what is the method to go from the Carleman estimate to the observability estimate? So what you do is you find some estimates for the weights e power AF. So e power AF, all these things. So if you have found the weights estimates for the weights, you can just ignore e power AF from the whole equation. Then you use energy estimates to get phi0, phi1 on the left hand side. So once e power AFs are removed, whatever you have is just the energy for the whole domain. So now if you use energy estimates, you can restrict whole domain to just one time slice. So on the left, you will have this. And if you take A large enough, then this will also vanish. So you will just be left with this thing, which is the thing on the right hand side. So that is shortly, like very briefly speaking, that is the main idea to go from Carleman estimate to observability. Obviously, technically it's extremely long, but this is the main idea. So that's why to solve observability, you try to find Carleman estimates. Okay. So these are just some references if you want to do like know about control theory. This is not just for waves; these are just general control theory references. So second one is available on the author's website for free. And I think one and the first and third are also available online. Okay. Before talking about how to like what the approach is, I'll just briefly mention the results that we have obtained. So in the first one, what we did is get some improved controllability results for wave equations, but in this space. So this is an extremely difficult problem because if you remember the duality thing that I was mentioning, so over there you had if I write like this, control and adjoint. So control problem which is y and adjoint is t. So if here I take L2 plus h minus 1 data, then this will be h10 plus L2. And it is easier to find a Carleman estimate lying in this space. However, if you take this to be h10 plus L2, then this becomes a really bad space, L2 plus h minus 1, and then it's extremely difficult to find Carleman estimate for these kind of spaces. So that's why if you consider a space like this, then it's a much more difficult problem. So that's what we did in the first one. And over there, the control region was time dependent. We will see what the region is. In the next one, we took domain to be time dependent. However, we had to lose something, which is you can only do controllability in L2 plus h minus 1, which is basically this one, but then it's this Carleman estimate, so it's slightly easier. And in the final one, this is the most general result we have, which is the whole geometry is time dependent. So it's a control result for waves on Lorentzian manifolds. You can basically think that I don't know how to, I mean, I have some figures, I can't draw Lorentzian manifolds, but you can think that everything inside the whole like geometry is time dependent. So a very basic example in this would be, instead of this, you consider something like this. You replace this Aij depending on x by Aij depending on t and x. And there are some assumptions on that, but they are very like natural assumptions that you have to take.
Even more general, right? Because here you are assuming at least the negative part of the matrix and the
yes.
Like general Lorentzian case can be more general.
Yeah, it is. So over here you can see this is a very step-by-step thing we did. So initial the first one, only the control region is time dependent, domain is static. The second one, the domain is time dependent as well, and in the last one, the whole geometry is time dependent, not just the domain. So right, if you have never seen Carleman estimates, then I'll just say this thing that they are deriving Carleman estimates is an extremely long process. You need to do like pages upon pages of calculations. It's very technical and it cannot be shown in a 1 hour talk. So I am not going to present any of the technical things because I myself don't like seeing it in talks. But I have tried to present some of the main ideas behind it. And to talk about those ideas, we first need to look at a simplified problem. And this simplified problem is basically the multiplier approach that we saw earlier. So what is this multiplier approach that was developed by Ho and Lyons? So let's say that you fix a point which is outside the domain and you have some r which is supremum of this thing. So it's basically telling you how far the point x0 is from the domain. There is a reason why these two things are in color. I'll talk about this in a bit. But if you wait long enough, then just for the wave operator, no lower order terms, observability holds with such kind of a region. So what is this region? It's clearer if you look at the picture rather than the definition. So what this is saying is that you draw rays from x0 towards the domain, and then you consider all the points at which the ray is leaving the domain. So anything between this part, those are the regions where the ray will leave the domain. And anything on the left part, that's actually the place where the ray is entering the domain. So you don't need to put anything there. You only need to put the control on this part. And then you just stack all those slices like this. So basically all the right, I won't say half, it depends on how you have put, but basically this part of the domain is the place where you need to put the control. And intuitively speaking, what is happening here is that let's say the domain is in front of me and I'm standing here. Then what are the places where inside the domain which I can see? So anything that I can see, I don't need to put the control. That the part of the domain which is away from me, that is the part which I cannot see. So that's where you need to put the control. Okay, so essentially that is what this is saying. So x minus x0 dot nu is just the normal at this point, right? So all these places where it is leaving the domain is the part where it is positive. That's why you need to put the control there. And remember this, that in this approach x0 lies outside. I'll most likely talk about this again after a few slides. Right, so how do you solve this? It's okay, in elliptic PDs and parabolic as well, there may be many different tools, but in hyperbolic, the most powerful tool that is there is integration by parts. So that's what we do. You take box operator acting on phi multiplied with some multiplier. So the multiplier that Ho and Leon chose was this type. So gradient of the distance function. So distance function is just x minus x naught whole square. So you take this type of multiplier. There is a zeroth order term, but that is not very important now. So you take this type of multiplier and then you multiply with this and then do integration by parts and energy estimates. So if you do that, you will arrive at an estimate of this type. So E of minus t is essentially some way just this thing. So after that, you take this on the left. So that's where you get the t minus r thing, that you need to wait sufficiently long enough so to get controllability. And on the right, what you have is this integrand, but on the whole domain. Now, I don't need to take the integrand over the whole region, right? I can just take the part where this is positive because this is on the right hand side of the inequality. So that's why you get this region, that the control region is just this part where it is positive, and then you put the control region over the whole time slice. Okay, so okay, this was the first thing, but the bad thing about this is that it does not apply to time dependent domains, which is what we wanted to do. So what is time dependent domain? It's basically this setting. So if you are talking about a static domain, it is like this. And if you want to talk about a time dependent domain, then it can change with time. So it's like a moving cylinder where each at each time slice it is some omega t. So we want to work on control problems on these kind of domains. So the main idea behind this is this notion of Minkowski geometry, which is I don't want to say generalization, but it is like an analog of Euclidean geometry, but corresponding to a different kind of metric. So Euclidean geometry in Rn compared with Minkowski geometry in R1 plus n. So over here, your distance is given by just the usual one we know. Over there, it is given by this kind of thing. So you have what you get from the Euclidean, but also there's an extra term coming from the time contribution, minus t tilde square. This is very important that there has to be a minus here. So basically this sign should be different from whatever you put here. You can put plus here and minus there, but either way it should be different. The metric here is again what we already know, and metric for the Minkowski is minus del t square, and then rest is from Euclidean. So naturally, what is the operator that arises here is the Laplacian. And similarly, what is the natural operator that should arise here is this wave operator. So that's why this kind of geometry is better suited to studying wave equations. And if you remember this x naught point that was there outside the domain from where you were seeing the domain, that was the reference point. But now that we have generalized to t naught x naught, it is something which is known as a reference event now. So if you hope to generalize control results for wave equations to time dependent settings, then best idea is to use Minkowski geometry kind of notion. Right. So how do you modify this multiplier technique for Minkowski case? So you change the reference point x naught to reference event t naught x naught. The distance function that was there earlier was x minus x naught square. Now it will be this type. There is some normalization factor, you can ignore it. But it will be of this type, square distance function corresponding to this metric. And the multiplier is, earlier we had, I'll just go back a few slides. Right, it was gradient of distance function acting on phi, but for us now it is Minkowski gradient of f acting on phi. So this part was already there, but now this part is extra, coming from the time component. And there is a minus here, but we still get a plus here because you get a negative from the metric as well. So minus and minus will give you plus. Again, this is the same that was there before. So now that you have all this, after that you just need to apply Minkowski integration by parts. And the new thing here is that you need to remember that when you do integration by parts, not just the spatial boundary, but the temporal boundary will also contribute. And over there, sign for the t components are going to be flipped. If you remember this, you can do integration by parts. I have a very quick, like just not full calculation, but just an illustration of how it's done. So let's say you start from here. In case if someone is not familiar, this is Einstein's summation notation. So it's basically just saying that you take derivatives into like twice. So it should be only when xi, xj, and then summing over everything. So if you have this, then do integration by parts. So the first and the third term is what you usually expect from normal integration, the usual one. That's why you have a minus here and a plus here, and this is the extra term that you will get due to using Minkowski integration by parts. So this is the bottom slice of the cylinder, this is the top slice of the cylinder, and again minus here because del T comes with a minus. So after that you do Minkowski integration by like finish it, and then you will get observability. And why are we doing this? Because this method is applicable for time dependent settings. Of course, we are trying to do Carleman estimate, which are kind of weighted integral estimates. So just taking this type of estimate is this type of multiplier is not enough. What we actually take is something like this. Okay, so if you remember in the like model Carleman estimate I showed, there were some e power af's in there. So they basically correspond to this f e power af that we have here, and then you do integration by parts with this conjugated operator. And one of the key requirements to get the Carleman estimate is this notion of pseudo convexity, and you can basically think that it is a kind of positivity condition, because when you want to prove estimates, you want to get like good signs for all the terms, right? So for this process, there is one term which we don't know if it has a good sign or not, and pseudo convexity ensures that it has a good sign. Okay, and then you can arrive at observability. So there was a problem while trying to do it with the usual distance function we took. So that one we had was somehow generalized distance to Minkowski. So it was this thing. However, this one is not directly applicable. So because again we need pseudo convexity, but this is not exactly pseudo convex. So what you need, there are two things you can do. One is you change f to some f epsilon, that is pseudo convex. You work with that, and then again because you have perturbability, you have to somehow come back. And the other thing is you change the metric itself. So f is not pseudo convex in the metric that you have, but you change the metric so that f becomes pseudo convex, and then work in this new metric. They are kind of equivalent in some sense if you think a bit. So depends on what kind of computations you want to do. So we have used both of these in different results, and you can see I am talking a lot about this f distance function, and there is a reason for that, which is this f is actually responsible for giving us significantly reduced control regions compared with previous Carleman methods, and because of which we want that any computations that you do with with this f, the computations have to be like really, they should go well with the geometry that you are taking. And this is done because of this notion of null coordinates. So over here I have written everything in Cartesian coordinates, but you can change the language slightly. So this is a language that comes from, you can say, Minkowski geometry or Lorentzian geometry. Over there, instead of taking x and t, they work with u and v. So u, v is basically these coordinates. So this is u, this line, and then this is v. So clearly f is just uv. So again over here computing derivatives of f is difficult, but this is very easy, right? So del u of f is minus v and del b of f is minus u. So all these computations become easier, and whatever control regions we get are heavily dependent on this cone. And this is not very different from what we study in usual PD theory. So this bottom cone is just the domain of dependence in wave equation. So anything, so what is happening at this point is dependent only on the points inside this cone, and anything that is on the top cone is being influenced by this point. So these are the domain of dependence and region of influence thing that we study in normal wave equation PD theory. So again, our control regions are restricted to the exterior of the null cone, and the control regions we get are of this type. So the first row is for static domains, the second row is for time dependent domain. If you remember, I had said that there was a, like when we talked about the multiplier approach, there was a point where we said this observation point is outside the domain. So that is what was being done before this, but for us we can actually take this observation point inside the domain as well. So if you do that, then this is the control region you get. So it's just this part, you don't need to put the control in the yellow part of the cylinder. So basically the whole cylinder is the domain, and you need to put the control only in this part, not inside the cone. And over here, this red region is the part of the cone, sorry, part of the cylinder which is exterior to the null cone. And I don't know if it's very visible, but so again, going back to this part, which is not visible to me. So if you stand at this point, then the top cone is known as the future cone and bottom cone is the past cone. So if I stand here, I can see everything that is happening here and also that has happened here. So I don't need to put the control on this part. Similarly, I don't need to put the control here. You need to put the control only on this part. So even this part is, you don't need to put the control. It's very difficult to like plot this and show on 2D. If I had 3D models, it would be easier, but correspondingly you get similar kind of figures for time dependent domains.
But these are not optimal. Sorry.
It's not optimal. I mean, so there are, it's like you gain something, you lose something. Optimal regions can only be derived by GCC microlocal, but microlocal cannot do anything if you don't assume analyticity. So if you think that way, then analyticity is there, not there. So that way it's the best control regions you can get.
I mean, you should say that like, he has done that.
Yeah, yeah. Yeah, it's not.
There is no theorem like that you cannot do or something.
So yeah, I guess so. What happens is when microlocal people are doing it, so there is a unique continuation result that they use. I guess if some other unique continuation result is derived, then it can be used. But all the ones that have been done till now, they are using Tataru's unique continuation result, and that is not applicable for without analyticity. So yeah, it's not a result, but till now nothing has been done using microlocal for like completely without any assumptions on analyticity.
But at least for wave equation using like Carleman estimate, can you derive the optimal control result?
I mean, so when this was done, this was the best one. After that, some other people have done a slightly better as well, but it's not known if that is the best one. Again, using Carleman only.
But can you recover the result of the equation?
Recover what?
Like using microlocal analysis, you have the optimal region.
Yes.
But now for wave equation, like we consider very like nice. I mean, you consider coefficients which are analytic.
Yes.
Okay, and then you try to use Carleman estimate.
Okay, then what this will give you is not optimal.
Not
because the way it is done is that you only do this if you don't have analyticity. If you have analyticity, it does not care whether analyticity is there or not. It will just give you what it gives. So that way, if you are doing it for analytic, then still microlocal is better than this. You cannot recover same ones from here. Okay. So as I was talking about earlier, so getting Carleman estimate in this kind of region, it's very difficult. If you have waves in good space, then adjoint becomes very bad, and then it's a very difficult observability problem. So in the first result, we were trying to do interior controller waves in this good enough space. That's why it was much more difficult to get the Carleman estimate itself. So for that purpose, we had to somehow derive a Carleman estimate for this operator known as ultra hyperbolic operator, which is not a very well studied operator. So you can think that this is kind of a generalization of wave to multiple time components. So it's just this one, and this is there for waves usually, but now you have T1, T2 up to Tm. So what we had to do was derive a Carleman estimate for this, and then we use a special case of this to get Carleman for the wave equation, and then do observability for that. And again, as we saw in the previous figures, the control regions we get, they are restricted to exterior of the null cone, and this observation point, it can be inside the, it can be anywhere, like inside, outside does not depend inside the domain. And as you were asking, so some further improvements were done to this using similar Carleman for ultra hyperbolic type operator. So what they did is, so it depends how much you want to improve. So for this one, it was like this. I think what they did is it's like this. So you actually only need like a full slice here. Other place it can be very thin. I mean, it depends. You can even make it thinner, but you only need a full slice near the place where you're observing from. So it's like, so this is the cone, and then you need a slice, full slice here, and rest places it can be very thin. There is some deception that happened, which is I showed the figures for boundary control, because if I do for interior, pictures are not at all like clear. But for interior control, remember the figure we had drawn, which was gamma. So for interior control, you take a tubular neighborhood of that gamma, and then so these two are for usual Carleman methods. So and then you stack. So that is the control region you get. But for us, this is the control region. So it's only the exterior of the null cone. Okay. So it's the part which is lying outside the null cone. You don't need to put anything. So if you want to put for bigger time of control, then you can see that this cylinder will be even longer. But for us, even if it's bigger outside, you still need to put control only on this part, not outside. Next result was, as I showed earlier, so you have time dependent domain control. Again, because you are making the domain general, you lose something which is only wave equation data in this bad space, and again control will lie in space of distribution. So this was interior control. Boundary control for this was obtained by my advisor in 2019. And finally, this is the most general result, which is for the Lorentzian case. So you have some smooth manifold, Lorentzian manifold Mg, and delta and R are the connection and curvature for G. And then you consider a wave operator of this type. So you can either think of it like wave operator on Lorentzian manifold, or you can just think of it the way that I have written here. So like a general second order hyperbolic operator, where G depends on T and X both. So there are some bounds we assume on R and del R. Under those assumptions, we get boundary controllability for these kind of operators. And this is done by getting a Carleman estimate for the Lorentzian manifold that we have assumed. And again, control regions are lying outside the null cone that we showed. And there is another like corollary, which is we get some unique continuation result, which has applications to inverse problems. So I don't want to go into inverse problems, but they are somehow related to Carleman estimates, and you can solve inverse problems using Carleman estimates as well. And very quickly, I'll just go through this. So there was a Carleman estimate for ultra hyperbolic type that I was saying. So using that, we have derived a uniqueness result for this type of operator. Again, this is very few people study these kind of equations because there are well-posedness issues. But depending on certain conditions, you can show that this equation of this solution of this equation can be determined uniquely depending on the boundary data and the interior data. So these are the results. But for further problems, I think I have written some of them. We are only working on the nonlinear because that's the most interesting one, both theoretically and application wise. One can try to weaken the curvature assumption we have in the Lorentzian case, but at least with what we have tried, it's not like you don't get a lot of improvement as of now. And this is the most difficult problem out of the three. So how do you, even the Lorentzian case we did was in this rough space L2 plus H minus 1. So most of the times when people talk about control of waves, they are actually working with L2 plus H minus 1. It's only when you do in the more difficult H1 plus L2, you mentioned that, okay, it's this difficult space, that's why we are doing it in a different way. But yeah, it's very difficult to do it for the good space for Lorentzian. And finally, some connections have been found between ultra hyperbolic equations and this notion of backscattering problem. I actually don't know much about this. I'm just working on it with a collaborator. So we hope to make some progress using the last result for inverse problems. I think I'm almost out of time. So there is this really nice pictorial or graph that I found online. You can go to this website. I think he's an engineer, but he does a lot of control theory, not mathematical, other kind of control theory. But it basically shows you how big the area of control theory is. And I think whatever we do, it's somewhere over here. There could be some other one or two things here, but yeah, it's just, and I can assure you that somebody who is working here has no idea what's happening in some other part. Even when I was doing my PhD, me and my PhD advisors, another student, both of us did not understand what the other one was doing. So it's a very huge area. And so I would like to stop here. Thank you.
Thank Vaibhav for a very nice talk. If you have any questions, comments, you can ask.
Is that verified numerical?
I actually don't know. So there is, I think these time dependent ones have not been verified. But if you talk about the previous older results that I showed, there are many results actually. So actually, very recently there have been some notes on it. I don't recall the papers, but in this there are other notes by Zuazwa that I mentioned. You can just search for I think it's called control and numerics, and over there they show. I am sure that for the older results there is, but for the new, like at least for the previous 5-10 years, I don't think the numerics are there. For the previous ones there is.
I mean, so like this time dependent domains, no numerics.
Yeah, I at least have not seen them. I think that's because people started doing numerics very recently, so it may be just a matter of waiting few years and then it will be there for other people. Yes. Yeah. Okay. Yes.
You have to do first theoretical and.
I'm sure somebody will do it very soon.
So, they like examples where you get anti-hyperbolic operators, which are,
Okay, so
or it's just to prove something. I mean, it's fine if it is just to prove.
so when I was doing it, I could find very few papers on ultra hyperbolic. I think there is some notion. I don't want to say things that are wrong, but there are papers that I read. They were talking about this from string theory papers are there, where they basically need this multiple time component thing. But in maths, I have not been able to find. So it's either there, and very recently, like maybe just at the beginning of this year, Professor Rakesh actually contacted me saying that ultra hyperbolic equations are there in backscattering problems. So backscattering is a type of inverse problem where you have some domain and you send some rays there, and then depending on how it comes back, you see what's the structure of the domain or what's the material. So I think over there also there is some notion of like not exactly directly applicable, but you can transform the system into something where ultra hyperbolic equations can be used. So in maths, I think this is the only one. And if you go to physics, there is a very good paper I can send you. So over there, they're talking about existence, because existence is a very difficult problem there. I only did the uniqueness part, but existence you have to have like several restrictions, and you can either do initial value problem or boundary. But if you put both, then it's I think very difficult to get there. But apart from string theory, I don't think there's any other applications I have found. Even that I don't understand.
It's a trick will not work. It's no longer just an OD.
No, it does not work. It's very
You
difficult.
cannot do it like OD.
Even 2 cross 2, it's very difficult.
Yeah.
I talked to many people, and
Yeah, how do you?
it's just because it's overdetermined, so you don't have anything to do. So I mean, it's very restrictive kind of thing.
Yeah. Can you add these analysis? Can you add just even critical selling terms?
Yeah, there are. So whatever I have showed, it's a very like niche kind of area. If you talk about just control of wave equations, it's a huge field, and whatever you were saying, there all kinds of terms are there. There's memory terms are there. There's coupling. There's even I think wave coupled with other equations, wave coupled with itself. Subcritical terms are also there. There's for nonlinear case, there's very few results that are there. But I think if you talk about one dimension, there's like quite old results are there as well, even from 90s. It's only that we are trying to do it for both n dimension and different like general domains that it's a difficult thing. But nonlinear, as far as I know, I think there's very like limited class of nonlinearity that you can do, not very general ones.
No, what I was asking, like that once you did,
Yes.
forget about the
Yes.
usual the domain, time dependent domain.
Yes.
So if you just add a like a semi-linear term, by power, but subcritical so that you can control by shoulder. Would it like is the method kind of robust or any kind of
So this, I mean, it depends. So the thing is, when you are doing this adjoint thing, the HUM that I mentioned, so there are two. You have to show that something is equivalent, right? So you have to go both ways. So as long as it is linear, there one direction is of that is very easy. Like people don't even bother about doing it because it's automatically there. You only need to show the other direction, which is basically observability. So basically, what is there is that you have to show something like this, and for wave equations, linear ones, this is already there, so you don't bother about it. You are only doing this. If you take some because the one that we are actually doing now, we don't have this one with nonlinear. So we have one with singular potential, and there it doesn't hold. So best we can do is just observability. Controllability cannot be obtained as long as you are working in the H1 L2 spaces I was talking about. If you want to do controllability with nonlinearities, I think you have to do with fractional Sobolev spaces, and I think that's a not that well understood as of now.
You mean to say, like, I mean, when you consider nonlinear problems, observability inequality does not imply convergence.
Yes. So I mean, it's, you have to go like, it's not enough to go from controlled observability to come back as well.
So are there any results for nonlinear?
Yeah, there are results.
Like controllability results.
Controllability results are there in very specialized.
How do they?
They are constructive, not like this.
Okay.
But they are fully constructed. You know, some of them are like take at the linearized operator. Just put the linearized one in. And then the other part is some sort of
Say something like forum or something.
I think that one is the hyperbolic systems.
It's like you have semi-linearity with nice enough estimates. Let's put the linearized operator.
So I mean, first semi-linear one was done by 90s. So it's after that, I think people have done some linear, like semi-linearities, and there are results on quasi-linear as well. It again depends on like what kind of assumptions you put. I think I would say that it's not like very general results are there, mainly because you don't have the second condition. First condition maybe you can do.
Any other question from the online audience? If you have any questions, you can ask. They're there or already left. Okay, if not, then we can thank the speaker and conclude.